Chapter 3, Section 4. Moving on to the next section in Chapter 3. Complex numbers. I kind of hinted at this the other day whenever we were trying to take the square root of a negative number. I mentioned imaginary numbers, correct? Complex numbers is another name for imaginary numbers. So we're talking about imaginary numbers today. All right.
Well, we need
Good stuff.
another day.
So,
We need a break.
the imaginary unit I. Not all quadratic equations have real number solutions like we saw in our previous notes and assignments. So, for example, we were trying to solve x squared equals negative 3. How would I get rid of that squared term?
Square root.
Take the square root of it, right? Whoa, that was awful. But when I tried to take the square root of a negative number, I couldn't find a number that multiplied by itself gave me a negative number, correct?
Yeah.
So I said no real solutions. You guys remember that? A little bit at least.
It's true.
So, because the square root of any real number is never a negative number. To overcome this problem, mathematicians created an expanded system of numbers using the imaginary unit I, defined as I equals the square root of negative 1. Write that down. I equals the square root of negative 1. Write that down. I equals the square root of negative 1. Write that down. I'm not asking, I'm telling you. Write it down. I equals square root of negative 1. I want you to also write down I squared equals negative 1. Because if I square both sides, I get I squared. If I square the square root of negative 1, it just becomes negative 1. So I squared equals negative 1. The imaginary unit I can be used to write the square root of any negative number. So now we can take the square root of negative numbers. Okay? Are there any questions about that? Can I move on or are we still writing? Okay, I'll give you some time. Okay, moving on. So, the square root of a negative number property. So here's the properties right here in 1 and 2. Number 1, if r is a positive real number, then the square root of negative r equals I square root of r. Let me show you why that is. So in our example over here, we have the square root of negative 3. Based on this slide, I know the square root of negative 1 is I, correct? Or square root of negative 1 is I. So I can break this down into negative 1 times 3 under my radical. And my property of radicals says that I can split those two numbers into their own radicals. So what did we say the square root of negative 1 was?
An imaginary number.
Square root of negative 1 is I. So that's why they got I square root of 3 for square root of negative 3. So everyone see that? That's how it's broken down. Huh?
That doesn't make sense still.
How does it?
Imaginary numbers?
So the square root of negative 3.
I is not a number.
Hold on. Square root of negative 3. I can break that up into negative 1 times 3, right? That's still equivalent. Right? Because negative 1 times 3 is negative 3. There's a property of square roots that says if I have two numbers multiplied under square root, I can split them into their own square roots. Okay? And based on what we've learned about imaginary numbers so far, the square root of negative 1 is I. So when I take the square root of negative 1, it just becomes I times the square root of 3, because the square root of 3 is not a nice whole number. So I just leave it as the square root of 3.
Why would you try to solve that though?
We'll try to solve what?
Negative 1 and 3 under the square root deal.
Well, if I multiply those, I just get back to my original square root of negative 3. Right? So there would have been no point in me doing that if I'm just going back to that. Right?
Then it would just always equal out up there. Why is
Well,
this
we're talking about
imaginary?
complex numbers now. We're no longer in just the real numbers. We're now expanding into complex numbers.
So
Okay?
unnecessary, bro.
So,
This is so
shh, please keep talking. That's part one of the property. Part two, by the first property, it follows that I square root of r, all that squared, just equals negative r. So here's another example. I square root of 3 squared. That would become I squared times the square root of 3 squared. What did we say I squared was? Negative 1. And then if I square a square root, the square and the square root cancel. So that just becomes 3. So negative 1 times 3 is negative 3. So that's how that's broken down. Okay?
We change it multiply.
Where'd the
3
I
and
go?
negative 1.
Say it again.
We change it multiply 3 and negative
Yeah, that's what we did.
1. No, like off the jump. Just like,
Yeah. I was just showing you what is happening for us to get to that jump. Does that make sense? Okay.
Where'd the I go?
I squared is negative 1, right? So this is I squared. So that just becomes negative 1. Okay? Are there any questions about these two properties?
A lot.
Can I go ahead and move on?
Yes.
Okay. Evaluate each expression. Example 1. Okay, so for letter A, we've got the square root of negative 25. Square root of negative 25. It's got a negative 25 under the radical, correct?
Yup.
So do I have any real roots here? Not any real roots.
But we do have some fake ones.
Imaginary. We don't call them fake. Complex numbers. So how can I break this negative 25 up underneath my radical?
Make 2.
What do we do over here for the square root of negative 3?
-1.
So it's negative 1 times 3, right? So what does negative 25 become?
5, 1.
Negative 1 times what? Negative 1 times 25, right? Underneath my radical. Does everyone see that? That's still equivalent, isn't it? So negative 1 times 25 is negative 25. Okay? What's the square root of negative 1? I. What's the square root of 25? 5. Does everyone see that?
Why did you put the
Say it again.
Why did you put the I from
The I after the 5?
5? Yes.
Because the square root of negative 1 is I. We learned that from this slide right here. Square root of negative 1 is I. Right? So over here, I take the square root of negative 1, which is I. Square root of 25 is 5. So I get 5i. Is anything staying under the radical? Or did I take the square root of everything?
You got it.
I took the square root of everything, right? Bear with me. So there's my answer. Any questions on letter A? Letter B. Square root of negative 72. On letter A, 25 was the number that I could just take the square root of, and I got a nice whole number, right? It was a perfect square. Is 72 a perfect square? Can I take the square root of it and get a nice whole number? No. So we're going to have to simplify our expression while we're still taking the square root. Okay? So we would get negative 1 times 72, correct? And the other day, we talked about simplifying square roots a little bit. Does anyone remember how we simplified square roots?
Don't we have to put one of the numbers outside of the group?
Yeah, how do I do that though? I did it two ways. First way was I looked for the biggest perfect square that went into 72. You guys kind of remember that or no? You do? Not really. What's the biggest perfect square that goes into 72? Does anyone know off the top of their head?
7.
7's not a perfect square.
7, 7. It's 49.
What'd you say?
9 and
9 is a perfect square, right? So 9 would go into 72. But I think there is a bigger one.
Squared.
Huh?
Not 9 squared.
9, I'm just talking about perfect squares. What are my perfect squares? 1's a perfect square. What's my next perfect square after 1? Not 2.
4.
I can't take the square root of 2 and get a nice whole number.
Oh.
4,
9.
9. You guys see how we're getting our perfect squares? What's 1 squared?
1.
What's 2 squared?
4.
3 squared?
9.
4 squared?
16.
5 squared?
5.
6 squared?
36.
7 squared?
49.
So everyone see how we're getting the perfect squares now.
Oh, so 36.
Those are all perfect squares, right?
Yeah.
So is there a bigger perfect square other than 9 that goes into 72?
36.
36 does, right? So I can break this down even further. Then negative 1 times 36. 36 times what will give me 72?
2.
2. Does everyone see that? Now I'm going to take the square root of the numbers that I can take the square root of. Can I take the square root of negative 1? Huh?
No.
You sure?
Oh, I.
It's I. So I'm pulling out an I. What's the square root of 36? 6. Can I take the square root of 2 and get a nice whole number? No. So it stays under the radical. Are there any perfect squares that go into 2 besides 1? No. So, this would be my answer in simplest form.
That's scary.
6i square root of 2.
That's not like I.
Remember, there was another way that I taught you. We could make a factor tree of 72 and break it down. What are two numbers that multiply to give me 72?
9 and 8.
9 and 8. What are two numbers that multiply to give me 9?
3.
3 and 3. What about 8?
4 and 2.
4 and 2. Is 3 a prime number? Are there any numbers that multiply to give me 3 besides 1 and 3? No. What numbers multiply to give me 4? 2. And 2 is a prime number. For square roots, I look for pairs of numbers. If it has a pair, I can pull it out of the radical. If it doesn't have a pair, I cannot pull it out. So I already took the square root of negative 1 is I. What do I have pairs of?
3s and 2.
Got a pair of 3s, a pair of 2s, right? So I can pull a 3 out and I can pull a 2 out. What's 3 times 2?
6.
That's what I got. And then this 2 does not have a pair, does it? So it stays under the radical. So that's a couple ways to look at simplifying a square root. Any questions about that? Questions on B?
Wait, so can you just do that like off the rip? You just do that?
Yeah, you can do it that way if you want.
That's a lot easier, it looks like.
Okay. Say, if I was doing it this way, I would go ahead and break it up like this. So you know you got to take the square root of negative 1 to get I. We still need an I out there. And then break it down like this. Pull a 3 out. Pull a 2 out. 3 times 2 times I gives me 6i. This 2 does not have a pair, so it stays under the radical. Does everyone make sense? Or does that make sense to everyone?
Where did 36 come from, though?
I broke down 72 into 36 times 2. Because that's 36 is the biggest perfect square that goes into 72. Does that make sense? So, the reason we pull pairs out is because this is understood to be a 2, square root. Square root's the opposite of squaring a number, right? So if this was a cube root, I wouldn't be pulling pairs out, I'd be pulling groups of 3 out. Right? So I'd pull out a group of 3 of 2s, but not a group of 3 of 3s, right? So, if it was the 4th root, I'd be pulling groups of 4 out. 5th root, groups of 5 out. So on and so forth. Okay? Today we're just talking about square roots, though. Questions on B? Okay, letter C. -5 times the square root of -9. I got a -5 outside. Do you think that's going to go away at all?
No.
It's going to come along for the ride. Okay? What would I break up -9 into? Well, first off, is 9 a perfect square?
Yep.
Yes, it is. So what can I just break this up into?
3.
No.
-3.
-1 times
3.
9. Right? If it's a perfect square, I don't have to do the factor tree. So I can take the square root of it. So, I've got -5. What's the square root of -1? I. So -5 times I. Times, what's the square root of 9? 3. Have I taken the square root of anything? Or everything?
Yeah.
So my square root's gone. I took the square root of everything. What's -5 times I times 3?
The answer, -5 of I.
15.
-15I. Because I can multiply the 5 and the 3, right? And then the I is just tacked onto the end. Questions on C? Is it making a little more sense? I know you guys still don't like the fact that there's a new set of numbers, but is it making a little more sense now the more we do?
I mean, it looks pretty easy.
I would like
I mean,
it more if it was.
On this example, the main focus was the square root of -1 is I. Everything else would take the square root of like normal. Okay? Questions on example 1? Moving on. Evaluating a power of I. This is really small to see, isn't it?
Yeah.
Okay, so I'll write it a little bigger. I squared. What is I squared?
Negative
That's
-1.
-1, right? That's what we learned on that first slide. I squared equals -1. Right? What if I give you I cubed?
What if?
Uh-oh.
Positive.
That would be
1.
I squared times I, right?
Okay.
I could break it down like that. So what is I squared?
1.
-1.
-1. So what's -1 times I?
0.
Just -I, right? Does everyone see that?
Kind of.
No?
I'm looking at charts. This is I.
So we all get understand the concept that I squared is -1. Now I have I cubed. I cubed can be written as I squared times I. So I'm multiplying something with the same base, I add the exponents. So what's 2 plus 1? Does everyone see how this is equivalent to this? I squared times I is still I cubed. But I know specifically what I squared is. What is I squared? -1. Right? What's -1 times I?
-1.
I. So I cubed is -I. What if I have I to the 4th?
Negative I squared. Well, I squared times
Hmm?
I squared times
Very good. It could be I squared times I squared. What's I squared?
-1.
So I get -1 times -1, which is just 1. Right? So I squared is -1. I cubed is -I. I to the 4th is 1. Does everyone see that? Anything to the 0 power is what? See if you guys remember that. What's anything to the 0 power?
0.
Not 0.
itself.
No real solution.
Anything to the 0 power is 1. So that's what this chart is showing you here. I to the 0 power is 1. I to the first power is I. I to the second power is -1. I to the third power is -I. And then that cycle starts over. When it gets to I to the fourth, it's 1. I to the fifth, it's I. I to the sixth, it's -1. I to the seventh, it's -I. That cycle just keeps going and going and going every 4 terms. Does everyone see that? So here's a little trick on how we can evaluate a power of I. So let's say they give you I to the 273rd power. We could evaluate what I is based on these rules right here. So to evaluate, you probably want to write this down. To evaluate a power of I, divide the exponent by 4. When the remainder is 0, my remainder is 0, the power equals I to the 0 power, which is 1. If I divide by 4 and the remainder is 1, the power equals I to the first power, which equals I. If I divide by 4 and the remainder is 2, the power equals I to the second power, which is -1. If I divide by 4 and the remainder is 3, the power equals I to the third power, which is -I. And I can do that because the cycle is going to keep repeating itself. So I just take my exponent, divide it by 4. Whatever the remainder is, I use that for the exponent on I. And I can evaluate it. So it's either going to be 1, I, -1, or -I. Okay? So do we need to see an example real quick to hopefully help us understand it a little better?
Yes.
Can I move on or are we still writing? Okay, I'll give you a little bit of time. Take your exponent, divide it by 4. You're going to get a remainder of either 0, 1, 2, or 3. Whatever your remainder is, you use that for i's exponent. And you know what these are, so that's what it would equal. Can I move on to our examples? So, evaluate I to the 27th power. I to the 27th power. So what do I need to do with my exponent here?
Divide by 4.
Divide it by 4.
Really?
Shh. How many times does 4 go into 27? 6. 6 times 4 is? 24. 27 minus 24. 3. So I get 6. Remainder of 3, right?
6.
What's my remainder?
3.
So, I to the 27th power just equals I to the third power, because that's what my remainder is. What's I to the third power?
C cubed equals C equals -C.
I.
Oh, I.
So what does I cubed equal?
-I.
-I. So -I would be my answer.
Smokes.
Does that make sense?
Now.
Yes.
So we took our exponent, 27, right? Divided it by 4, just like it told me to do. Right? To evaluate a power of I, divide the exponent by 4. Does that make sense? So I took my exponent, 27, divided it by 4. 4 times 6 gives me 24, because 4 goes into 27 6 times. My remainder is 3, right? When the remainder is 3, the power equals I to the third power. So that's why I write I to the 27 equals I to the third power, which equals, I know I to the third power equals -I.
So the answer is just going to be that.
My answer is -I.
Like, that's just all it's going to be.
What?
That, what you did.
What I just wrote up here.
No, not that. I'm talking about the answer is going to be.
It's going to be one of these 4 options. Yep, it's either going to be 1, I, -1, or -I. Every time. Because like it shows on this chart right here, that pattern just keeps repeating every 4 units. Okay? So, let's do another one real quick. Say I've got I to the 54th power. I to the 54th power. What do I do with my exponent?
Divide that boy by 4.
Divide it by 4. How many times does 4 go into 54? 13 times? Well, it can go into 5, can it? How many times? It goes into 5 once, right? We forgot to do that. It's 4 times 1? 4, right? 5 minus 4? 1. Bring down your 4. How many times does 4 go into 14? You told me earlier. 3. 4 times 3 is 12. 14 minus 12? 2. So 4 goes into 54 13 times. What's my remainder? 2. So I to the 54th power equals I to the 2nd power, because that's what my remainder is. Right? What does I squared equal?
Negative 1.
-1. So there's my answer. Does everyone see that?
Why did you do that step? I don't get why.
Which step?
When you are subtracting stuff.
Here?
Yeah, I don't.
This is just division that you guys learned in elementary school. Yeah, it was a long time ago, wasn't it? That's just division that you learned in elementary.
Put it in my calculator.
Yeah, you can.
Good luck with that.
But you got to figure out your remainder. That's why I do the long division like this. Okay? Do I need to do another one, or are we kind of okay with that now?
We are good.
All right?
I'm ready for this assignment.
Can I move on?
Oh my
Okay,
goodness.
standard form of a complex number. A complex number written in standard form is a number a plus bi. You need to write that down. A plus bi. Complex number written in standard form is a number a plus bi, where a and b are just real numbers. The number a is the real part of my complex number, and the number bi is the imaginary part of my complex number. So complex number consists of a real part and an imaginary part.
So BI is imagination.
Yep. A is the real part, bi is the imaginary part. So know that a plus bi is standard form of a complex number. You need to know that. If b does not equal 0, so b is any number other than 0, then a plus bi is an imaginary number. If a is 0 and b is not 0, then a plus bi is what we call a pure imaginary number, and it's just some number I. That's what we call a pure imaginary number. The diagram over here shows how different types of complex numbers are related. So my real numbers will be of the form a plus 0i. There's no imaginary part of it. So they're just wholly real numbers, right? So a plus 0i would be numbers like -1, 5/3, pi, square root of 2. They have no imaginary part to them, so they're just a real number. Imaginary numbers are numbers like 2 plus 3i. They have a real part and an imaginary part. 9 minus 5i, real part and an imaginary part. Pure imaginary numbers, their real number that makes up the imaginary number is 0. So they just take on the form some number I. So -4i, 6i, so on and so forth. Okay? The main thing I want you to take away from this is how to know how to write standard form of a complex number. A plus bi. A is the real part, bi is the imaginary part. Okay? Questions on standard form of a complex number? We okay with that? Can I move on? Or not? Okay, I'll give you some time. I'm moving on. Let's talk about adding and subtracting complex numbers. Hey, this part is easy. How about that? So, shh, quit talking. To add or subtract two complex numbers, add or subtract their real parts, and add or subtract their imaginary parts separately. So it's essentially like combining like terms. Okay? The real parts I combine together, the imaginary parts I combine together. That's my answer. So the sum of complex numbers, if I have a plus bi plus c plus di, I take the real parts, a and c. Does everyone understand that those are the real parts, a and c? And I add those together. I then take the imaginary parts, add them together, and that goes in front of I. And then that's my answer. You're combining like terms. It's going to make more sense once we do an example together. A minus b, or a plus bi minus c minus di. Remember, if we have a negative in front of a set of parentheses, we need to distribute our negative. Right? So, it would distribute to the c and to the di, and then I would combine like terms. So before y'all get too confused about this, I go to an example to where it's easy. Letter A. 8 minus I plus 5 plus 4I. It wants me to add or subtract, depending on what it tells me to do. And it wants me to write the answer in standard form. What is standard form again?
A plus bi.
Right? A plus bi. The real part comes first, the imaginary part comes second. So, 8 minus I equals, or plus 5 plus 4I. I'm adding my complex numbers, correct? So do I have anything to distribute to my sets of parentheses?
You might.
I don't. So I can drop my parentheses here. I'm going to tell you this. We're going to treat I like a variable. So what we're going to do here is just combine like terms. So what do I have like terms of? I's, the negative I
And positive numbers.
and the 4I. Those are like terms, correct? Those are both imaginary parts, so I can combine them. So it's negative I plus 4I, 3I. What's another set of like terms?
Wait, would that not be a
Wait.
negative? Oh, wait, it is. Oh, my. Sorry.
Question. 8 and 5 are also like terms. What's 8 plus 5? 13. Can I combine 3I and 13? No, they're not like terms. One's imaginary, one's real. So I'm almost to my answer, but is this in standard form? Nope. There would be my answer. Is everyone okay with adding? Is that easier than what was presented to you on the previous slide?
Can we switch
Yes.
the other way to where that answer automatically comes out?
Yep. If you went straight to 3I plus 13, or 13 plus 3I, that'd be okay. Does everyone see that? For letter A. We okay with that? Pretty easy. Combine the real part, combine the imaginary part. Combine like terms. Can I erase A and move to B?
Sure. We only even got 5 minutes left.
You'll be okay. Letter B. I've got 7 minus 6I minus 3 minus 6I. I've got a negative there in front of one of my sets of parentheses. What do you think I need to do with that negative?
Distribute.
It's like a negative 1 times my parentheses, correct?
Yes.
Is my first set of parentheses going to change at all?
No.
No, so I can drop those parentheses. But I've got to distribute this negative to this other set of parentheses. Everyone okay with that concept? So it's negative 1 times 3.
Negative 3.
Negative 3. What's negative 1 times negative 6i? Positive 6i, correct? So since the real part always comes first in standard form, let's combine our real parts first. So it's automatically in standard form when we get it. So what are my real parts here? 7 and negative 3. What's 7 minus 3? 4. Everyone okay with that?
Yeah, what happens now?
What are my imaginary parts?
-6i.
Negative 6i
And positive 6.
and positive 6i. What do I get when I combine those? 0i. So if it's 0i, do I need to write it? So my answer is just 4. Does that make sense? We okay with that? Combining like terms, right? That's all it is. Letter C. Looks a little different, but we can still do it. Got 13 minus 2 plus 7i plus 5i. So what's my first step here? It's the first thing I need to do on C. Not distribute 13. What's immediately in front of that set of parentheses?
A negative.
Negative 1, right? So I just have to distribute that negative to the set of parentheses. This 13 just stays. What's negative 1 times 2? Negative 1 times 2? Huh? Negative 1 times 2? Negative 2. Negative 1 times 7i. Negative 7i. And then I have my plus 5i. Okay, what are my real parts that I need to combine? 13 minus 2. What does that give me? 11. What are my imaginary parts that I need to combine? Negative 7i plus 5i. What does that give me? Negative 2i. Is that in standard form? Can I combine anything else? There's my answer. Is adding and subtracting pretty easy? Combine like terms. Distribute the negative if you have a negative in front of your set of parentheses. Okay? That's where we'll stop for today. We'll finish up tomorrow, get the assignment tomorrow. Are there any questions about the notes we took today before I end the recording?